Hello everyone, welcome back to Diksha Karnataka YouTube channel, and today I am going to discuss Decode NCERT chapter Wave Optics. And if you are following this series from the beginning, then you should know that here we are trying to help you to understand the NCERT book in terms of chapter wise, in terms of concepts. Also I am going to discuss the concepts briefly, not in detail. For detailed explanation you can watch my KCET series, or you can even check my Brahmastra series where I have done a lot of detailed discussion. But anyway, here if you are starting to study for your competitive exam or any other exam where you are confused between the lines, where to study, what not to study, here I am helping you to guide the most important parts from each and every chapter. And the most important part of this lecture series, to attend this lecture series you have to have your NCERT book along with you. So Wave Optics chapter is in the part 2 of your NCERT book. If you have not yet opened it, please open it and then follow me through this journey. Okay, so Wave Optics is an important chapter in terms of concepts. A lot of question comes in the exam, not in the PU board exams, but it is super important for all the competitive exam. This is a very highly important chapter for this is a favorite chapter for all the competitive question paper setters. Now in the introduction part you can skip most of the introduction. Nothing is important in the introduction part. You can just have a read about history of light and optics, how they have started, okay, what is the background of this. So you can just have a read how Newton and Descartes started with the journey of corpuscular theory of light. Okay, Descartes is basically the person who is responsible for your Cartesian coordinate system. Okay, so that Descartes was initially gave the corpuscular theory, then Newton developed on that, then Huygens came and Huygens gave the wave theory of optics. But unfortunately during that point of time Newton was so powerful, Newton's concept, because he is a very he was like a god of physics at that point of time. So people ignored Huygens for a long time till another person came and he developed from the Huygens principle. Okay, and Huygens principle is now what is commonly known as, he is the pioneer of wave theory of light, and from there we have built entire chapter from that, right? So if you don't want to study this chapter, you have to go back in time and kill few people so that this chapter is deleted, right? Hopefully not, just a joke. Anyway, wavefront, first of all let us start about the basic concept of wavefront. Huygens started his principle by saying about wavefront. So what is a wavefront? Wavefront is defined as the surface of constant phase. Surface of constant phase means a surface. It can be a plane surface, it can be a curved surface, does not matter. It can be a circular plane. So whatever it is the locus of all the points having same phase, or surface having constant phase. Both are same definition. Okay, I like to say in terms of locus. Locus means the points that you join, it is the path that it traces. Okay, it can be a 3-dimensional, it can be a 2-dimensional, but in this sense surface means only 2-dimensional, but it can be a circle as well. Even though circle is a 2-dimensional object, but circle itself is not a surface, right? Circle is a line. If you join the line, the line is itself is the circle. So there are different things, and one example of wavefront is when you drop a stone into the pond or into the water body. I know in your childhood everyone has done this. Okay, if there is a lake around, if there is a pond around, you will take a stone and throw it to the pond, right? And you will see some ripples happening in the water. Now the circular ripples that you see are basically a wavefront. Okay, and they propagate from the source. Source is where you drop the stone, so that is the source, and slowly you will see that the ripples are coming out. So that wave that is being generated, they are all at the same phase. That's why it is like a wave front. Okay, if you go to a seashore, you will see the waves coming at you. The wave which is coming at a time, that wave is actually a wave front. Okay, and there are different wave fronts in the sea, right? So this is a basic example of wave front. Now let's look into the Huygens principle. Each point of the wave front is the source of secondary disturbance, and the wavelet. Wavelet means what? Wavelet means is the small waves which is being generated from the wavefront. Okay, wavelet means child of wavefront. Okay, child of wavefront we will discuss in a while. So basically wavelet means small wavefronts. Wavelets emanating from this, emanating means emitting, basically emanating from this point, spread out in all direction with the speed of the wave. So he is saying very simple thing, that suppose there is a wavefront. This is a wavefront. Okay, this is a wavefront means this is a wave coming at you. Now he is saying that at any point on the wavefront is basically source of secondary wavelets, and these secondary wavelets can emit in all possible direction. Okay, this is a simple thing. So basically he is saying that even though there is suppose this is the source of light. Okay, light is traveling towards this. Now what he is saying, that this light, any point on that wavefront means same phase, light can this can be considered as a secondary source. Okay, secondary source can again behave like a primary source and can emit light in all possible direction. Now there is a some flaw. Some flaw means light cannot travel backward, so that part was left by the Huygens to interpret it. That's why many people said, okay, because Huygens wave theory is wrong, because he is saying light is traveling backward, which is not possible. So how it is correct? Okay, so that's why people actually started rejecting it instead of trying to correct this statement. Okay, later on Fresnel came. Fresnel is another very prominent scientist. So later Fresnel who corrected Huygens principle, and it was known as Huygens-Fresnel principle. Okay, so he was another physicist working in the same field of wave theory, and he was also done a lot of work in Huygens principle as well. Then there was Fraunhofer. So they all corrected this theory instead of correcting the theory at that point of time when Huygens was working on this theory. Many people rejected it, saying that it is not possible. But anyway, we will see that why what are all the important parts. So these wavelets emanating from the wavefront usually referred to as secondary wavelets. Okay, so secondary wavelet, there is a question from this, what is a secondary wavelet, as a MCQ. Okay, secondary wavelets are basically emanating from the primary wavefront. Okay, the whoever is coming out of the secondary primary wavefront is called secondary wavelets, or secondary wavefront as well. Secondary wavefronts and wavelets are basically same thing. Okay, and if we draw the common tangent to all these spheres, we obtain the new position of the wavefront at later time. So if you consider all such points, okay, and if you draw a common tangent to them, okay, then you will get a secondary wavefront. So this is slightly complicated in terms of understanding. You will understand this better if you study physics in your higher class. But anyway, it is very easy to understand the basic principle, that all the points on the secondary primary wavefront actually behaves as a secondary source, and they emit light in all possible direction, or they emit waves in all possible direction. They all travel with the same speed as the wave. That was also part of the objective question. The speed of secondary wavelet is half that of primary wave. It is same as primary wave. It is 1/4 of the primary wave. It is double that of primary wave. It is same as the primary wave. So don't fall for the trap. You have to remember that the speed is always same as the primary wave. Now refraction through plane wave, the derivation is given here. You can study from this, or you can follow my Brahmastra series where I have discussed in detail about this derivation. So the derivation is sin I by sin r is equal to v1 by v2, and after doing all this, you can get the Snell's equation, that is n1 sin I is equal to n2 sin r, right? Again there are given it for another portion. So first we have done it for rarer to denser, then refraction at a rarer medium from denser medium. So this is the condition for critical angle. Again, this is not required. You can study from the previous one only, and only thing that you have to remember that for critical angle it is n2 by n1. n2 is the refractive index of the rarer medium, n1 is the refractive index of the denser medium. In general, n2 is air, so n2 is given 1, so sin theta IC is equal to 1 by n1. Based on that, lot of question comes, so you have to remember this concept. Otherwise, this derivation is not required, only the first derivation is required, the second derivation is just a part of it, right? Next is reflection at a plane wave surface. Again, this is also a common derivation. 3-mark derivation often comes from this chapter. Maybe it will be given as a part question of your 5-mark question, or it can be given as an individual 3-mark question. So this is a very common question as well. Again, the derivation is covered in the Brahmastra series. Now this is a very interesting question. I see once or twice this kind of images. Okay, so it is a plane wavefront. Plane wavefront is represented by a single line, and after it refracted through a prism, okay, it bends like this. We know that after it passes through a prism, what happens to the light? We have seen that in the prism diagram in the ray optics chapter, that after passing through it, it bends towards the base. So bend towards the base means after passing through it, it bends like this. So this is the now shape of the new wavefront. So they sometimes ask that draw the ray diagram or draw the wavefront when it passes through a prism, lens and a concave mirror. So these are the three things: convex lens, concave mirror. These three are the application or explanation of the wavefront principle. So when plane wavefront passes through a prism, it remains plane, but it becomes at an angle. Okay, the angle changes. It is no longer parallel. So this is very interesting. And for a convex lens, okay, it becomes a spherical wavefront. Okay, spherical wavefront of radius f, but it bends like this. Whereas in case of concave mirror, it again becomes a spherical wavefront, but it bends like this way. Okay, so it is no longer a plane wavefront in these two cases. So maybe it can come as an objective with the different images given for the same diagram, or it can be come as a 3-mark question or 2-mark question as a part of your PU board exam, right? So this is very important to remember these three diagrams. These three diagrams are part of your course, so you cannot ignore that. Many students ignore this, but it is easier to remember and understand, so that's why. And also it is asked, I think one of your blueprint paper was there where this question was asked. Now this is a test. This is a ripple tank test where you are generating two waves and you are trying to overlap them, and you are watching what is happening. Okay, so there are two things called incoherent and incoherent addition of wave. What is the meaning of coherent? Coherent is basically when the phase relation between two waves are fixed and not changing with time. It is called a coherent wave. What is the meaning of phase relation? Phase relation means, suppose you are standing in a queue. Very simple to understand the phase. You are standing in a queue and someone is standing in front of you, someone is standing behind you. Okay, and during the COVID, you know that you have to maintain a 1 arm's length. So you are maintaining 1 arm's length with the forward person, and whoever is behind you is also maintaining 1 arm's length with you itself. Whenever you are going ahead, the person who is moving ahead, he is also maintaining the 1 arm's length. So everyone is maintaining 1 arm's length amongst each other. So basically there is a phase relation. So if this thing is continuously going on between you and the person in front of you, person behind you, then it is called a fixed phase, and this is a fixed phase relationship. So basically it is a coherent line. Now you imagine you are standing in a queue of railway ticket counter, or in some temple where you are someone is jumping ahead of you, someone is trying to overtake you. Sometimes the distance is varying, you are just standing behind you, and the person goes ahead ahead, and you realize, okay, the person has already moved ahead, I have to move now. So if you are doing like this, the motion between the people are not constant, it is changing with time, then it is called a incoherent source. So similarly, if two waves generating from two different sources, okay, coming to meet at each other, and if they have this kind of fixed relationship, they are called coherent source. And if these two sources, they do not have this fixed relationship, they are changing with time, then this is called an incoherent source. Most of the things that we see are incoherent sources. For example, if you lit up two different lights, okay, mostly they are incoherent. Okay, there are few ways to create coherent sources, but that is a very specific way. Otherwise, most lights are incoherent in nature. Okay, even as if you consider a tube light, okay, if you consider a LED tube light, okay, even the portion from the left and portion from the right, they are not coherent. Single tube light, they are different portions are not coherent with each other, okay, because of the different molecular vibration, right? So this is also an example where incoherent sources can be there. Okay. So incoherent sources are possible in many ways. One coherent example of coherent sources is laser light. Laser light also has multiple sources. This is not a point source, even though it appears to be a point source. It consists of multiple sources within that laser light. Now in case of a laser light, all such points, if you point a laser at some point, okay, all the points inside that one single laser light can be considered as coherent sources. So these sources are coherent sources. If you somehow can make them separate, you can consider two separate coherent sources. So laser light is one of the example of coherent sources. Now here we have two coherent such sources, S1 and S2, okay, and they have some fixed phase difference. Okay, so here they have shown that the phase difference is path difference. In terms of path difference, they have shown path difference and phase difference, they are linked. No, don't worry. Path difference in a sense is that the 1 arm's length, I told you 1 arm's length between you and your forward person, 1 arm's length between you and your backward person. So that is a path difference. And phase difference is basically time, how much time is there between you. So that is a how much time, so if you want to move into his place, how much time it will take. So that is a phase difference. So we will take about that as well. Okay, so a path difference, if the path difference is fixed, then it is called coherent source. If path or phase both are same, okay, they can be converted from one to another. So maybe you are getting confused, sir, you are saying path difference once, you are saying phase difference once. For right now, you have to imagine that they are brothers. Okay, they have some relationship amongst them, so you can convert from path to phase, phase to path. We will see that in a while as well. Now, so if you somehow overlap lights of having fixed phase difference, okay, sometimes you will get the intensity of the light 4 times. So this is very, very interesting. Sometimes you are getting light of intensity 4 times, and sometimes you will get intensity 0. Okay, that is called interference. The interference terms comes from this part. Interference is nothing but superposition when two waves meeting at different position. Okay, if they are meeting with in phase, that means if one of the wave is high, other wave is also high, they are increasing the intensity. So like this, in this case, if you see both of them are meeting with high point together, so that is called high point. So that is a constructive interference, that is the intensity is increasing. And if one is high, another one is low, so in that case, when they are interfering, their intensity is getting decreased. So this is a destructive interference. Based on different positions, you will get this kind of thing. Okay, this is happen when two different sources meet at a point. Okay, now, so there is this derivation is there. It is not super important, but you can check through this if you want. Now if the path difference, in terms of path difference, if the path difference is a integral multiple, integral means, as we know, integral is 0, 1, 2, 3, they are called integers. So integral means integer multiples. If the wavelength of light, basically we are using monochromatic light, this is very, very important. Monochromatic light is very important. If you are using monochromatic light, okay, and when they overlap with each other, if the path difference between the two waves which is merging with each other, that is the integral multiple of wavelength lambda, then they will give you a constructive interference and the resultant intensity will be 4I naught. So this is very, very important. If the interference is happening when the two waves are meeting with each other with same phase means when the path difference is lambda, they are giving you high. They are giving you a high intensity, that is called constructive interference. Now, if the path difference is integral multiple of n plus half into lambda, I don't like to use it like this. I like to use it like 2n plus 1 lambda by 2. Okay, this is the way I like to write it. So if it is again 2n plus 1 lambda by 2 multiple of like that, then it is a destructive interference, and again it can be start from 0, 1, 2, 3, you can put 0 here. So this is called destructive interference and the intensity is 0. Now here we are assuming sources are coherent and they are like you have studied in superposition of waves in your PU1, when two equal amplitude waves are coming from opposite sides, similar thing is happening. Two equal amplitude light, coherent light, they are interfering. They are not coming from opposite side, they can come from any angle. Opposite side is not necessary in this case, okay, and you are getting a very interesting pattern, okay. The pattern we will see in a while, and in terms of this is called phase difference. So I was talking about phase difference. So this phase difference, in terms of phase difference, the intensity can be given by 4I naught cos square phi by 2. Okay, and the relationship between path and phase difference will be given somewhere, we will see that. Okay, so phase difference can be pi plus minus pi plus minus 3 pi plus minus 5 pi, which is corresponds to the condition given by equation. We will have a destructive interference. If it is 0 plus minus 2 pi 4 pi, so if it is an even multiple of pi, then you will get a constructive interference including 0, and if it is an odd multiple of pi excluding 0, you will get destructive interference. This is the basic condition. Okay, so this is in terms of phase difference. Now let's move on. Now Young's double slit experiment, very common. So what he has done, okay, he has taken two sources. Now this is incorrect, this part is incorrect. What he has done, he has taken only one source of light. He has taken only one mother source of light, and then he has created two slits. Slit means cut. If you cut the paper with a very small, very sharp blade or your razor, okay, then whatever you see, that is called slit. Slit is very, very thin opening. Okay, so here he has one slit, and this is a top view. From the front view, slit is looking like a line. Okay, it will be just like a line. Okay, so he has created two slits. So this is slit number 1, this is slit number 2, slit 1, slit 2, this is from the front. Okay, and behind these slits there is a single source of light. Okay, and from this single source of light, the light is coming, and they are basically divided into two different sources. So one source, sodium lamp, he is using one sodium lamp, and now he is dividing it into two different sources. The sodium lamp can be considered as a coherent source, and from there he is dividing into two sources, so they have a fixed phase relation. Okay, now you can consider according to Huygens principle, as he said, all the points on the secondary wavefront can be considered as source of secondary wavelets. So these are these secondary wavelets, you can consider them to be individual sources. So now they are interfering at some point, and you are observing that interference pattern that we have discussed about. Okay, and based on that, So this is the source, this is correct diagram. So this is the source, here is S1, here is S2. Okay, this is the distance from the this is called central point, central fringe. We will see what is fringe, and this is the point of observation, and if you observe it, you will get some interesting pattern. Now there is a condition of interference. The condition for interference is basically x d by d is equal to n lambda, or if the distance that you are measuring, is of the order of n lambda d by d, then you will get a constructive interference. This is a very important, tumba important for all the competitive exam that you are going to appear. So you have to remember, this is the condition for constructive interference, whereas this is the condition for destructive interference. Okay, so lambda d by d is common. Okay, if it is n lambda d by d, it is constructive. If it is 2n plus n plus half into n lambda d by d, then it is a destructive interference. Okay, so whatever formula you can want, I generally write it like this: 2n plus 1 by 2 lambda d by d. Okay, now capital D is the distance between the slits and the screen. Here it is a screen where you are observing. Okay, and small d is the distance between the sources. Small d, as the symbol suggests, small d is very small, whereas capital D is large. Okay. Now there is a thing that I have observed, that students often forget which d is first, which d is in the division, which d is in the numerator, which d is in the division, and student often write the opposite thing, lambda small d divided by capital D, which is a completely mess. So how to remember that? How I used to remember that lambda is wavelength. Wavelength is very small number, right? It is in the terms of nanometers, right? It is in the nanometers, angstrom, like that. So lambda is very small for light, whereas d is a bigger number. It is maybe in centimeters. So d is in centimeters or even in meters. So d is a smaller number, and this small d is in millimeters. Okay, micrometers, even in micrometers or millimeters. Okay, so you have to remember the smallest number with the largest number. Okay, divided by the middle smallest number. So lambda is the smallest number, capital D is the largest number. Okay, it is because it is in centimeter or in meters, and small d is in between lambda and d, so that is the division. This is how I used to remember. The smallest number has to be multiplied with the largest number. Okay, and then you divided it with the medium number. Okay, that is how I used to remember. I still remember like this. Even if you just give me the problem, I might get confused sometimes. Okay, so that's how I remember the things. So you also, I hope you will remember like this. Now this is a way to this is called a fringe pattern. These are called fringes. Okay, so this is a dark fringe, this is a bright fringe. So if you complete this experiment, what you will get dark and white bands like this. Band means the friendship band that you wear, or the same thing like that. Okay, if you cut it and if you see it, that is called a band, right? So this is a band structure. So if you see, this is a black band, then a white band, then another black band. So this is alternating bands and almost at equidistant. So you will see, this is the pattern, this is the Young's double slit pattern. Okay, if you do this experiment in your laboratory, obviously white will not be there, but it will be bright. Okay, white, generally you don't get white, because if you are using with yellow light, sodium is yellow light, so you will get yellow and dark consecutively. Okay, it will be very beautiful. If you get a chance in your laboratory, whenever you are doing in maybe in BTech or maybe in physics, if you are doing it, you will observe it. It will very mesmerizing. Okay, next is diffraction. Diffraction is slightly complicated concept, even though nothing complicated is there in your syllabus anyway. So diffraction is basically bending of light around a sharp object. So if there is a sharp object like a knife or a sharp edge, light bends around that. So basically when we say light, we generally expect that light travels in a straight line, right? In our previous chapter, in the ray optics chapter, we studied only the light travels in a straight line. If there is a, suppose there is a object, sharp object having sharp edges. Okay, we have an object with sharp edges. Sharp edges means suppose like this. Then what we are expecting if we illuminate it using some light? So what we are expecting is that light will pass through this and we will get some shadow region over here. Okay, so if you join like this, we will get a shadow region. If you remember in your class 6th or 7th where you have study about it, okay, shadow, right? So shadow region we are supposed to get it, but if the edges are sharp, instead of getting the shadow, we will get some region in the shadow where we will get some light as well, which is very, very interesting. Okay, why it is happening? This is happening because as we learned in the Huygens principle, that any point in the primary wavefront behaves like a source of secondary wavelets. So these points can behave as a secondary waves, and they actually behaves as a secondary sources, and they can emit light in all possible direction. So light can travel in this direction. Okay, that is the main reason. Here what we do actually, instead of using a sharp object, we do with a sharp opening, small and sharp opening. So here what we have done, we have similar things. This is a sharp edge, this is a sharp edge, and we have a small opening. This is called single slit diffraction. Young's double slit is using 2 slits. Here it is only 1 slit. Okay, there is an experiment as well, you can see. And once you do this, there is an experiment, I think in the later part, yes, this one. So there is a blade, top part and bottom part, if you can arrange like this, and if you pass a laser through this, you will get a beautiful pattern in the wall. Okay, this is a single slit, only 1 slit is there. Okay, so this is one experiment, and if you observe it on the wall, you will get a pattern like this, a very, very bright and wide central fringe. This is called central fringe. In the interference pattern also, whatever was the center at the center of the screen is called central fringe. Okay, central bright fringe. Here also it is called central bright fringe. In both cases, center will always give you bright fringes. In case of interference, in case of diffraction, you will get center as very bright fringes. Okay, and here you will get as you are progressing up and down, you will get slowly fading bright fringes. Okay, in between there is a dark region. Okay, and the width of the central fringe and the intensity of the central fringe is maximum. This graph represents the intensity. Okay, so as you can see, the intensity of the central fringe is the maximum, and slowly as you are moving away, the intensity is decreasing. Okay, so central fringe is very wide and very bright, whereas this is the expected one. This one is the expected. If we ignore these two parts, we are only expecting a central bright, very bright pattern, right? We are not expecting anything in the shadow region, right? The shadow region, you can try it using a torch light or a mobile torch. If you have normal opening, you light up, you will see only one bright fringe. You will not get any other fringes on the right or left. But if you use a laser light into the sharp opening of a blade, you will get that pattern that we are talking about here. Okay, now, so as you can see, intensity is decreasing as you move away. Okay, and they are not equal in width. Okay, so in case of interference, the width was equal. In case of diffraction, widths are not equal. Okay, no one has ever been able to define the difference between interference and diffraction satisfactorily. This is in terms of explanation. Explanatory difference, there are a lot of difference obviously, but explanatory difference is not super interesting. Okay, so if you can give any proper difference between them, maybe you can get a Nobel Prize in future, right? Anyway, let's move on. In interference and diffraction, light energy is redistributed. If it is reduces in one region, producing a dark fringe, it increases in other region, producing a bright fringe. There is no gain or loss of energy, which is consistent with the principle of conservation of energy. Very interesting. So light does not destroy or create anything. It is basically the redistribution of energy. So diffraction and interference, you might see that, okay, some black fringes are coming, that means they are destroying each other. Some bright fringes are coming, that means they are constructing each other. Actually no, it is basically redistribution of energy. Energy cannot create or destroy itself. Okay, now next part is polarization. So polarization is where we know that light can have multiple axes of propagation in the same direction they are propagating. It can propagate like this, it can propagate like this, okay, it can propagate like this. So there are multiple ways a wave can travel in a same direction. This is a two-dimensional diagram, so might be you are thinking, okay, wave always propagate like this, but wave can propagate like this also. Okay, wave can propagate at any angle. So even if I suppose this is my wave propagating, if we rotate it, there are a lot of, you will not understand any difference, right? Even if I rotate it, the wave is still propagating in the same direction. So based on the axis of this wave, okay, this is called unpolarized light. If there are multiple axes present in the direction of light, okay, this is called unpolarized light. But if you can somehow organize all the waves in the singular plane, like the way we draw in the paper, right, all the waves are aligned in the single direction, then that is called a plane polarized light. All the lights, all the axis of propagating light is in the same direction, then it is called plane polarized light. Plane polarized light is represented like this. Okay, y is equal to a sin kx minus omega t, so only 1, and the lambda is given by k 2 pi by k. This is the wave equation, we know that. Okay, so they have given some explanation, but not super important. Now the very important part from this is the intensity of light as given by I naught cos square omega cos square phi. So what is polarization? Polarization is when you pass that unpolarized light through certain crystal, okay, tourmaline or quartz, okay, there are different types of crystal, polarizing crystal. If the light passes through those crystals, okay, the light axis of the light align themselves in a particular direction, that is called plane polarized light. Okay, so this is called polarization of light. Now if you place one polarizer, that crystal is called polarizer, tourmaline or quartz. So this is the polarizer, light is passing through the first polarizer. The intensity of the light after passing through the first polarizer, you have to remember that for competitive exam, after passing through any single polarizer, the intensity of light becomes I naught by 2. This is the first polarizer. This is the first thing that you have to remember. Now suppose I already have a polarized light. I already have a polarized light of intensity I naught. This light is already polarized, and if you suppose the axis of this light is like this. This is the axis of the light. Now you have another crystal whose axis is not aligned in the direction of this plane polarized light. Okay, it is making some angle, say, so this is the original angle, so this is making, say, some angle theta. So if this makes an angle theta, what will be the intensity of the light after it passes through this second this new polarizer? Okay, so first you have obtained a polarized light. Okay, you have obtained a polarized light. Now you have this polarized light of intensity, say I naught, is passing through another polarizer. Its axis is not matching, it is making an angle of theta. So in this case, the light after it comes out, it will not be zero. The intensity will not be zero. Okay, it will not block all the light, it will allow some light to pass through it, and that intensity will be given by I naught cos square theta. Okay, this is very, very important, and this is called Malus law. Based on that, every year one KCET question comes every almost last 6 to 10 years. I have seen whatever paper I have seen, I have found one question based on this, and in that case they have give you 3-4 polarizers. First one will be an unpolarized light. So unpolarized light, when is entering the first polarizer, the intensity will become I naught by 2. Then from there on you have to consider the angle and use this law multiple times to calculate the final intensity. Okay, remember that one thing. And then we have the application of polarides. This is very, very common. 3 marks question, 2 marks question. Polarides can be used to control, and sometimes MCQ question as well. Polarides can be used to control the intensity in sunglasses, wind panes, etc. Polarides are also used in photographic cameras and 3D movie cameras. So these are the application of Polaroids. They are, if you are wearing a sunglass, costly sunglass, generally they have a Polaroid to block some light to give you comfort in your eyes. Now there is a summary, you can read this. Okay, there is no dimension in this chapter, there is no new quantities that we have learned, so no dimension and the points to ponder, you can read them. And we have now reached the end of this chapter, and let me know if you have any other comments, any other doubts in the comment section below. And if you have not yet subscribed to our channel, don't forget to subscribe to our channel. I'll be back with another chapter very soon.